Okay, strange title, normal data or not normal data. Very odd kind of title for probably the most important and the most challenging of the lectures in this class, in this course. Once we get through this, you've probably done the hardest part. And we were trying to understand how we can make predictions from a data set. That's really what we want to be able to do. We want to understand whether something is probably true or probably not true. And if it is probably true, how probable is it, or how not probable is it? Okay. If we know how probable something is, then that means we can make predictions about it, which is something that's finally useful. All right, we want to know what we can expect in the future, and science is probably the best way to know what we can expect in the future if it's applied correctly, because it gives us a way of looking at what has happened, and then rather than just a feeling that we get about what might happen, we can measure the exact probability or the near exact probability of something happening again. So this is where it starts to get interesting and useful. If we're reviewed up to now, we've kind of looked at descriptive statistics. We've summarized and described our observations. We've sort of made descriptions of our data set, or possibly the population that we've measured, our samples. We've made histograms of their lengths and things like that. We've said what we've found. We're going to use inferential statistics. We can make inferences, and the same observations that we use to be able to describe a population or a sample, we can now use as a basis for making estimates, making predictions. So this is where we get into the useful part. And so everything that you've learned up to now becomes a very good foundation for how to make estimations and guesses about what will happen in the future. So we've got a couple more more definitions, because you love definitions. And you probably heard me say these things and have some intuitive sense of what they are over the course. Population, that's all possible individuals. So if you have the population of, we were measuring smokers earlier in the class, and lung function based on smoking. So if we were studying women and their lung function, the population would be all women. Okay, and then we could take a sample where we take 100 smokers and 100 non-smokers. That's our sample. But we're generally not able to measure the whole population. We're not going to be able to do a lung function test for all women, but we can do a sample. We can do lung function tests for a sample. And a parameter is a number that describes a population characteristic. So if we had the mean air capacity of all women's lungs, that would be a parameter. But if we only have a sample and we're looking at the mean air capacity of those women's lungs that were in the sample, the ones that we tested, that would be a statistic. And so that's the whole reason this course is called, or used to be called, statistics, or you're going to be taking using lots of statistics in biology. That's what we're doing. We're using we're describing our samples, and generally we only have a sample, not the whole population. So before we go on into the new material, we want to stop and reinforce what we've already learned. If you actually go ahead and stop the video and do this exercise, all of these terms which are relevant will be cemented into your mind a little bit. The definitions will be more at hand, more easily recallable, and you'll get a lot more out of the lecture coming up. So take the time to stop, write an hypothesis that will answer the question above, which is more of a statement, and want to conceptualize the experiment. So the question: when we analyze the data, giving women control over the number of children, finances of families, and choice to work or stay at home seems to be the best way to raise living standards in all societies. So if you think back to the global warming exercise that we did, you can't write one hypothesis that is going to, well, you can, but it's difficult to test one hypothesis that answers such an overarching question. This is no different. You're going to have to write an hypothesis that will contribute. So maybe you do just something just with birth control, or maybe you do something with turning over the finances of families to the control of the woman, or working or staying home choices, something. In any case, do that and then figure out what the dependent variable is, the independent variable. Is it observational or experimental? All of this stuff in the experiment that you conceptualize, and you'll get a lot more out of this lecture. So my hypothesis, I wrote about control over the number of children, and it became mean household income will be higher in households where women can access free birth control. If you wanted to convert that to an if-then statement, which a lot of people like to do for hypotheses, it might be: if women can access free birth control, then mean household income will be higher. So you don't have to have an if-then, but any good hypothesis can probably be converted into an if-then statement. So parameter: mean incomes of all families globally. So if you see the statement up above, it says to raise living standards in all societies. So the parameter would be the incomes of all families globally. Globally is all societies. So think through and just see, you can see what my answers were here and compare them to yours, but in the interest of time, we're not going to go through all of those. Do a little bit of a review there. Then after that, you can go ahead and do these two quizzes on Moodle. Okay, let's get into the meat of this lecture. All right, we're going to be able to make predictions, and that's what we want to be able to do, make predictions. Then that's when our science becomes useful. It lets us learn and grow and make things and know that how they'll work, or what speed gravity is going to draw down the plane that you're getting into, all of that kind of thing. So we're looking at whether data is normal or not normal in order to be able to tell us how useful our predictions will be, or give us probabilities anyway. So what's normal and not normal? Normal, other names for them are parametric and non-parametric. Okay, normal data is parametric. Not normal data is non-parametric. We're not going to spend a lot of time on non-parametric data, but I'll just define it a little bit in these next few slides. In the meantime, normal data is something that we can visualize with a bell curve like this. And when we measure something like length, time, size, weight, etc., and plot it onto a histogram, if we have a normally distributed data set, that means that some of the some of the individuals will be around the on the high side of the mean, and some on the low side of the mean. But in general, the majority of them will be close to the mean. Okay, so close to the mean, or yeah, close to the mean in terms of measurement. So if you're measuring possum tails in the chi-mis, here's the mean length. The further away from the mean length, the less individuals that are going to have extremely long or extremely short tails. This is just like a histogram. Let's give you an example of something that is normal. If you drop these ping pong balls straight over this target, straight down, imagine that you've made it so it's perfectly vertical drop. There's no wind in the room. There's nothing. The ping pong balls are perfectly evenly weighted. They should bounce up and down, up and down, up and down, up and down, but maybe just by random chance they will slightly bounce to one side or the other, and you mark where each of them fell, the distance from the bullseye that each of them fell. Okay, so there should be a random distribution. Lots will just go straight up and down in the middle, and a little fewer as you go out, and the further and further you go out, the less observations that went that far, like here, and also the less probability that they will go that far in the future. This thing is called a Galton board, which is built to estimate it, and it has a probability for each of these beads as they come down this little chute of going either 50-50 of going one way or the other, and you'll see that most of them as they fall will wind up making this normal distribution curve. Here is a URL for the Galton board, and I encourage you to stop now, go to the Moodle page and get this URL and watch the Galton board as an example of a normal curve or a normally distributed data set. It's very helpful. All right, another example. If you went to the lab and you carefully measure out 5 milliliters of liquid, okay, are you going to get it exactly the same amount every time? You'll have a gradation on your vial that'll say 5 milliliters, just like a measuring cup. You've got a cup of flour, but it's not going to be exactly the same amount of flour grains in your cup of flour every time you do it. Sometimes it'll be a little high, sometimes it'll be a little low, and if you repeat that process a lot of times and you weigh it, you'll sometimes get just a little bit more than the 5 milliliters, which would be 5 grams of if it was water, and you will make a histogram and you should have a normal distribution, unless you're biased in some way that you're weighing heavy most of the time or something like that. So as long as it's not biased, you should have a normal distribution. Another example, if you go to Terry Island and go to Terry Matangi Island and measure the weight of adult tui. Some will be a little bigger, some will be a little smaller, but in general they'll be pretty close to the mean weight on average. And then the further away you get from the mean weight, higher or lower, the less chance that you're going to get a giant or a mini tui. That should be normally distributed if you put them on a histogram, the weights. So that's what a normal data set is. And then we have non-normal, or this one would be paranormal, but non-parametric. Non-parametric data, we're not really going to work with it. There's not much to know at this point except that you would do a slightly different statistical test in order to account for the variability that happens with a non-normal and non-parametric data set. So we have normal or parametric data statistical tools like t-tests and ANOVAs, and we also have non-parametric statistical tests. We're going to mention those, but we're not really going to get into them in this course. But you should be able to recognize that your data set is non-normal. So you could do an experiment and you tried your best to get enough samples, but you ran out of time or the boat sank or something like that, and you could only get so many samples. And it kind of looks like it's normally distributed, the blue lines on this histogram, but you're not really sure if it, maybe you had some sampling bias that picked up a lot of a lot of small, um, what would you call it? Samples, small lengths or something like that. And if you do the mean on this, it means that you're gonna the mean is going to be skewed over here from what the true mean would be by all of these high preponderance of smaller individuals. So if it's, we're not sure if it might be skewed like that, or if it was due to bias in your sampling method. That could be non-normal. Or, but you may have like a histogram that looks like this, and somehow you just missed out on sampling certain parts of the population. And in fact, this is a normal distribution, but it doesn't look like it. So we have tests in order to be able to try to recognize what non-parametric data looks like, what if it's not normal. But I'll show you some examples of how those histograms, those plots might look. It might look something like this, where you have, when you plot it, it looks like this. It's not a symmetrical bell curve, and we call that data skewed data. So they might have large outliers or extreme observations. If you have ranked data, 1 to 10, first, second, third, etc., highest, smallest, that kind of thing, that would be non-normal. Okay, so if it's ranked like categorical, then it's not going to be normal. Or yes/no data, that's more categorical. This is more discrete. Okay, then those are things that you can't really call a normal data set. Our data, if we're going to call it normal or not normal, generally it'll be it'll be a continuous data set. So here are some examples of non-normal data sets, or how we might visualize data sets. And if something is more spread out on the right, like in this case, we've got salaries. So we'll have a lot of salaries down at the bottom and a few salaries going up to the CEO and the management. And the mean salary is somewhere here, but it is more spread out on the right. Okay, so lots more examples on the right. Okay, so that is one way, and it could be spread out more on the left. Like, okay, so lots of people, not very many people die in Australia, not many men die, but once you get up to the 70, 80 kind of range, then lots of people are dying in that area, in that zone, and then a very few people make it to 100. So that is spread out on the left, okay? And you can have something arbitrary, like where if you roll a dice, you might get there's no rhyme or reason. There's no like pattern to the spread. It just happens that you get one where you're rolling 3 dice that or actually it might be 4 in this case. So they go up to 6 and the numbers add up to 14. Okay, so actually that would have to be a 20-sided dice to make it, because well, anyway, so this doesn't really have a pattern at all. It's arbitrary, okay? Or maybe in this one you could have like a multiple peaks. So let's say you have a couple of cohorts, like we've talked with our fisheries examples. You can have multiple peaks, okay? So these are different ways that something could be non-parametric, not normal. But we can also have a normal data set. And I would encourage you to go to Moodle and look up this URL and go to Khan Academy. There's a nice little tutorial, another example if you're tired of my stammering away, where they've described a normal data set. It might be helpful. Okay, a couple more quick examples before we go on and describe what a normal data set is. So length of time before someone looks away in a staring contest, length of pickled gherkins. Okay, if you measure them, the mean length will be right there in the middle, and some of them will be bigger and some of them will be smaller, but they hopefully will fall away around the they'll be about the same that are bigger and about the same that are smaller. They'll fall away symmetrically if you put them in a histogram. Here we go. We kind of understand what a normal distribution, what type of data set we'd be measuring that would have a normal distribution now, hopefully. So what is normal distribution? It's essentially a mathematical abstraction. It's a model. And you can think of it like a histogram where it's got a bell-shaped curve and there's the mean in the middle. And then, okay, so bell-shaped, like we said, bell-shaped, and asymptotic. So that means that as far as these lines go, theoretically, they will never actually hit zero. They'll never hit this line. So there's always some probability that no matter how far away from the mean you are, that you can find one sample that is that far away from the mean, that far of an extreme. But anyway, asymptotic at the extremes, just in the model, and bell-shaped. Okay, it's also symmetrical around the mean. So here's the mean. That's the mean tail length of all possums in the Kaimais or whatever it is that we're measuring. And it should be the same shape on this side and that side going away from the mean. Okay? The mean, the median, and mode all have the same value. So if there are the same amount of individuals that fall above the mean and the same amount of individuals that fall below the mean, the median should be exactly where the mean is, and the mode, the most individuals of that, or the most, whatever that measurement is, the most times that you should get that measurement should be right in the middle as well, which means right at the mean. So the mean, the median, and the mode should all be exactly the same, theoretically, in a perfectly normally distributed data set. All right, it can be specified completely once the mean and standard deviation are known. So we can calculate the standard deviation of our data set, and I know that's a little bit abstract, but here, this hopefully will help you visualize it. Okay, so what that means is the area underneath the curve, so all of this area is directly proportional to the relative frequency of observations. So we could calculate how big of an area this is, how many square centimeters it is, or whatever it might be that whatever we choose to measure it in, the area. And that should be proportional to how many observations we've had. Again, I know that's abstract, but bear with me. Here we go. So if we've got a perfectly normally distributed bell curve, normally distributed data set, and we know that the same amount of observations will be happening above the mean and below the mean, then we know that 50% of the observations will fall below the mean and 50% above it. And we also know that 50% of the area under the curve will will fall to below the mean and 50% above it. Okay, so that's the area under the curve. And essentially what we can do with this is we can say then that the mean, where 50% fall above and below it, the probability of getting an individual that is at least as big as the mean is 50%. Okay, so 50% of all the individuals we measure will be at least as big as the mean, and 50% will be higher than the mean. Okay, so we can figure out where on this curve something lies, and we can use the amount of area underneath the curve to figure out what the probability is that we sample something at that rate. Okay, we'll carry on. So here's another example of it. So 85% of the scores fall below score X. There we go. So if we're looking at a normally distributed scores on an IQ test or something, then 85% of the scores will fall below that spot X on this when we plot it onto a histogram. And also 85% of all the area under the curve will happen to the left of the X. Okay, so there's an 85% probability that your score, or that somebody will have scored below you if you score X. So that also means that there's a 15% probability that somebody will have scored higher than you. So if you're getting this, you might realize now, we're getting really down to the really important stuff. If you get this, you might realize that a histogram of normal scores could be like, if it's got a very small standard deviation, might be straight up and down like this, or a really big standard deviation, it could be something that would go like that. But the amazing thing is that if there's our mean, both be normally distributed. But the number of standard deviations is like the probability relates to the number of standard deviations in exactly the same way, no matter what the shape of the curve, no matter how wide the curve is. So all normal curves have this property. The standard deviation cuts off a constant proportion of the distribution of scores. Okay, I know that's a mouthful, but we're going to have another look at that. Okay, so if you go one standard deviation away from the mean, and we've calculated the standard deviation, so if we say the mean is 20, let's say, and the standard deviation is 3, S equals 3, then we know here that should be a score of 23, right? And then we can calculate what percentage of the area under this curve is. We don't even have to calculate it because there are tables that give that the math has been done for us. We can calculate what percentage of the area underneath the curve is greater or lesser than a score of 23. So that'll give us the proportion of scores below 23, and also the percentage of people that scored below that mark of 23. So one standard deviation, no matter what the standard, no matter how wide the standard or the normal curve is, 68% of all the scores will fall between one standard deviation above it and one standard deviation below it. Okay. We're going to have lots of practice. Don't panic. Okay, 95% of all the scores will fall within 2 standard deviations of the mean. So that means 95% of people will score within 2 standard deviations of the mean. If an IQ test is the mean is 100 and the standard deviation is 15 points, if you score above 130, then you are smarter than 95% of the population, plus this 2.5% over here, plus this extra little bit over here. So you're smarter than 97.5% of the population based on that score anyway. All right, so 99.7% of all observations will be greater than, or will be within 3 standard deviations of the mean. So anything like 145 IQ plus would be very, very rare. Okay, so 0.3% only would fall further than standard than 3 standard deviations away from the mean. So if an IQ test mean was 100 and the standard deviation was 15, then only 3 people in 1,000 would score better than 145. Okay, this is a repeat of that same information. Okay, there we go. Same thing that we were just talking about. Anyway, it's time to call it a day on this lecture, because that's a lot of material. But what you really need to do is reflect on this, and hopefully you can see how we can use the number of standard deviations away from the mean in order to make predictions about what the probability is that anything that we measure will fall somewhere on this line. So for any new individual that we measure, we can find out, or we can predict where they're going to fall on this line. And that's how we, as we cement this information with practice, hopefully you can you can pick up on how this really is such a useful tool in science.